In today's lesson, we are talking about congruency, so let's just begin with the definition. To be congruent means to be exactly the same in size and shape. Meaning that if I've got two congruent line segments, then they're the exact same measure. So if I have line segment AB and line segment CD, these two are congruent if they are exactly the same in measure. Similarly, I can have two angles like angle G and angle F, and these two we would call congruent if their measure was exactly the same. So let's say this was 30 degrees and this was 30 degrees. That means that angle G would be congruent to angle F. And this is how we draw congruency, that little equal sign with a squiggle on top. Similarly, if AB was 5 centimeters and CD was also 5 centimeters, that would mean that line segment AB is congruent to line segment CD. So to be congruent means to be exactly the same in size and in shape. Now the second definition that I want to be talking about today, just to make sure we are fully understanding, is the word corresponding. Corresponding parts are parts that match up in similar or congruent shapes. So, corresponding means parts that match up in similar or congruent shapes. And we'll get to see some examples of that in a minute. All right. Pause for a moment, make sure you understand those definitions, and we're going to move on to the next part now. Okay. Now, when we're talking about congruency, we need to be able to talk about what makes two things congruent. I can either measure every single part of these triangles, so to make sure that AB is equal to the corresponding part, ED, that BC is the same exact length as that corresponding part, DF, and that AC is equal to that corresponding part, EF, and then also that every single one of those angles match up as well. That's one way to check for congruence. Another way to check for congruence is to use rigid motions to show congruence. Now, we've already seen these three rigid motions. They are translation, reflection, and rotation. To show that triangle ABC is congruent to EDF, instead of measuring every single part, if I can show that a translation, reflection, or rotation can get me from triangle ABC to EDF, then I can prove that they are congruent. And so here I'm going to use my translation rigid motion. I'm taking ABC and translating it on to EDF, and if it maps directly onto it, that means it fits perfectly on top of it, that means that ABC is congruent to EDF. So I can say triangle ABC is congruent to triangle EDF by translation. Notice that I put the corresponding letters in the exact same order. So because I started naming my triangle as A, B, C, if I started with A, I need to start with the corresponding letter E. So A and E are corresponding letters, meaning that they're in the same spot of these two congruent triangles. So I'll start with A, that means I have to start with E. Similarly, if I start with B, or if B is my second one, then D should be my second letter. And finally, C and F, they also match up as well. All right, let's move on to the second example. I'm going to show that these two triangles, TRQ and TSQ, are congruent. And the way I can prove that is by using one of my rigid motions. So here I'll take my little patty paper, I'll put it over TRQ, and if I try to translate, it doesn't work out. If I try to rotate, maybe it works out. That could potentially be it, but I also see just a reflection over here. And if I reflect over this line TQ, I find that it maps perfectly onto that other shape. So I can show this by saying I did a reflection over the line TQ. So I can show that triangle TRQ is congruent to triangle TSQ by reflection. And again, notice I named this TRQ. I go along this diagonal line over here, starting at T then to R. So that's why it matches up. T matches up with the T in the front. S and R are the corresponding parts of my triangle, because when I take my original triangle and this is R, I'll put a dot on that R over there. When I reflect it, that dot is now matching on S. That shows me that R and S are corresponding angles or corresponding points on these two triangles. So that's why I have TRQ, and I'm going to call this triangle that is congruent TSQ, and I showed that by reflection. Now, the final example we're going to look at in this video is seeing how I can prove that triangle RST is congruent to triangle UVT. So maybe I'll put one dot next to the R over here, two dots next to the S, and three dots next to the T, just so that I don't mistake which triangle, what points are matching up. Now if I take this, translation doesn't really do. A reflection also isn't going to do me too well. But if I do one single rotation centered around point T, I can see at 180 degrees that triangle RST maps perfectly onto triangle UVT. And notice that my one dot was on R, this one little dot over here, and after that, that same point is over U. So that means that R and U are corresponding points. Let's take a look at the two dots. The two dots here end up on top of V. So now I know that S and V are corresponding points. And of course, T corresponds with itself, and those three dots stay there after the rotation. Three dots on the T, three dots still on the T after I'm done with the rotation. So I will finish off this video just by saying that triangle RST is congruent to triangle UVT by rotation. And that is it for this video. Hopefully that helped you with getting to learn a little bit about congruency and corresponding parts of triangles.